If you followed along with part 1 of this video, then you have built a major moon appropriate to the planet it will orbit. If you're coming to this video without having seen part 1, I highly recommend that you go back and watch that first, as it contains a lot of important information that we're going to need in this video. Link in the description below. In this video, we're going to focus on how to place our major moon into orbit of our chosen planet. The first and most important parameter that we need to define is our moon's semi-major axis, that is, the average distance at which it orbits its parent planet. When placing a major moon around a planet of any type, it must be placed between two very important boundaries, the Roche limit and the Hill radius. The Roche limit represents the innermost boundary and is the distance, measured from the center of the parent planet, at which the tidal forces will be strong enough to rip apart the moon. So your moon needs to be well above this critical distance. As a rule of thumb, it's best to have your moon orbit at more than 2.5 times the Roche limit, but several times this distance is even better. We can calculate the Roche limit using this equation, which equates the limit to the radius of our moon times the cube root of 2 times the mass of the planet divided by the mass of the moon. To make the math easier, I'm going to do the equation a bit out of the order given here. In the calculator, I'm going to start by entering a 2 and then multiplying by the mass of my planet, in parentheses. Then divide and enter the mass of my moon, also in parentheses. Your equation should look something like this. Then I'm going to press equals and take the cube root of this value by raising it to the power of 1 over 3. Press equals and then multiply the value by the radius of my moon, in meters. Now when I press equals, I get the Roche limit of my moon, also in meters. As you can see from the equation, the Roche limit is not just based on the mass of the planet, but on the mass and radius of the moon as well. So each of your moons will have a different Roche limit. Usually though, once you've placed the innermost major moon, you don't have to worry too much about the other moon's Roche limits, unless the next moon out is significantly more massive than the innermost moon. But the most massive moons typically orbit much farther away from the planet. The Hill radius represents the outermost boundary and is the distance at which the gravity of the parent planet is not sufficient to hold on to the moon. A moon placed beyond this distance would not orbit the planet, but rather the system's star. Unlike the previous equation, the Hill radius is dependent only on the properties of the parent planet and the system's star, so you only need to do this equation once to ensure that your system of satellites is within the boundary. The Hill radius is equal to the semi-major axis of the planet's orbit around the system's star times the remainder of 1 minus its eccentricity multiplied by the cube root of the planet's mass divided by 3 times the mass of the system's star. Once again, I'm going to do the math slightly out of order to make it simpler. I'm going to start by entering the mass of my planet in parentheses, dividing, opening another parentheses, and entering 3 times the mass of my system's star. Then close the parentheses. Your equation should look something like this. Press equals and then raise the value to the power of 1 over 3 to get the cube root. Then we multiply the result by the semi-major axis of our planet's orbit around the star, in meters. I'll then multiply again and open parentheses, entering 1 minus the eccentricity of my planet's orbit, then close the parentheses. Your equation should look something like this. Press equals and there's the Hill radius of your planet. Make sure all of your planet's moons are well below this distance. If you're building a major terrestrial moon, then it doesn't matter at what distance from the planet you place your moon, so long as it is beyond the Roche limit and less than the Hill radius. The distance only changes the moon's orbital period and its angular diameter as viewed from the planet. That is, how large it looks in the sky of your planet. So you have 3 options. You can just randomly pick a distance to place the moon at. You can place it based on the angular diameter you want it to have, or you can place it based on what orbital period you want it to have. To place your moon based on its size in your planet's sky, you can use this equation, which sets the distance to 57.3 multiplied by 2 times the moon's radius divided by the desired angular diameter in degrees. For reference, Luna has an average angular diameter in Earth's sky of about 0.53 degrees. So you can multiply this number by however much larger or smaller you want your moon to appear. If you want to place your moon so that it has a specific orbital period, you can use Kepler's third law to find at what distance it must orbit. But before we get to that equation, it will save us a lot of complication if we go ahead and calculate our moon's standard gravitational parameter. This is just the gravitational constant times the sum of the mass of the planet plus the mass of its moon. On the calculator, we start by opening parentheses and entering 6.6743 times 10 to the power of negative 11. Close the parentheses and multiply. Open two parentheses and enter the mass of your planet. Close one parentheses and add. Open another parentheses and enter the mass of your moon. Then close both parentheses. Your equation should look something like this. Press equals and then write this value down or save it in the calculator's memory. Now that we have that, we can use this equation, which relates the cube of the orbital distance to the desired period squared multiplied by the standard gravitational parameter divided by 4 pi squared. In the calculator, we start by opening parentheses and entering the orbital period we want our moon to have in seconds, and then raise it to a power of 2. Then multiply by the moon's standard gravitational parameter before closing the parentheses and dividing. Open another parentheses and enter 4 pi and raise it to the power of 2. Then close the parentheses. Your equation should look something like this. Press equals and then get the cube root of this number by raising it to a power of 1 over 3. That's your moon's semi-major axis in meters. Alternatively, if you choose to simply pick an arbitrary distance for your moon's orbit, you can calculate its orbital period using this equation, which equates the square of the orbital period to 4 pi squared times its semi-major axis cubed divided by its standard gravitational parameter. In the calculator, open a parentheses and enter 4 pi squared times the orbital distance that you chose in meters and raise it to the power of 3. Close the parentheses, divide, and enter your moon's standard gravitational parameter, also in parentheses. Press equals and get the square root by raising it to a power of 1 over 2. Press equals and that's your moon's orbital period in seconds. After recording your moon's period, you can convert the seconds into hours by dividing them by 3,600, or into days by dividing them by 86,400. If you want to determine your moon's angular diameter at that distance, you can use this equation, which equates its apparent size to 57.3 times twice your moon's radius divided by its semi-major axis, both in meters. Placing major moons around a Jovian planet is a bit trickier, as you are likely going to be placing several of them. There are basically two methods for doing this. The easiest is to place the innermost moon at some distance above its Roche limit, and then place the next moon at a stable distance beyond that, working your way out in order until you have all of your major moons placed. However, if one of your major moons is meant to be a habitable world, then this method isn't optimal. In such circumstances, you will likely want to have control over the moon's rotation period, as that governs the length of its day. And because your major moon is tightly locked to the planet, its rotation period will be equal to its orbital period, and that orbital period is dictated by how far from the planet it orbits. Therefore, you would want to place that habitable major moon first at the distance that gives you the desired orbital period, using the equation that we covered a few moments ago, and then place the other major moons at stable distances above and below it. For the ordered method, start by calculating your innermost major moon's Roche limit and set its semi-major axis to some multiple of that distance. We will then need to determine what the minimum stable separation is between that moon and the next one that will orbit farther out. To do that, we use this equation, which relates the minimum stable separation to the cube root of the sum of the masses of your two moons divided by 3 times the mass of their parent planet, then multiplied by 4 times the semi-major axis of the inner moon. In the calculator, start by opening two parentheses. Enter the mass of your inner moon, close one parentheses, plus, open another parentheses, enter the mass of the outer moon, and then close both parentheses. Divide and open another parenthesis. Enter 3 times the mass of your parent planet and then close the parentheses. Your equation should look something like this. Press equals and then get the cube root of this number by raising it to the power of 1 over 3. Press equals again, then multiply this number by 4 times your inner moon's semi-major axis in meters. When we press equals, we get the minimum amount the two orbits should be separated by. Add this to the inner moon's semi-major axis to get the minimum stable distance, and then set your outer moon's semi-major axis to some value above this. You then repeat these steps with each moon working outward. Yeah, it's a lot of work. Sorry. If you are instead starting with a habitable moon, use the equation shown earlier to calculate the semi-major axis required for it to have the orbital period you want, then work outward from its position, placing the moons that orbit beyond it. Once those are in place, come back and start working your way inward from the habitable moon's position by subtracting the minimum separation value from the outer moon's semi-major axis to get the minimum stable distance, and setting your inner moon's semi-major axis at some distance below this. Now, if all this feels too complicated or time-consuming, there is a simpler method you can use for placing your moons, which I call the double time method. The issue with this method is that it's sloppier and doesn't give you as much freedom in the placement of the moons, because basically it overestimates the distances in order to ensure that the moons are far enough apart to be stable. To use this method, you simply take the orbital period of the existing moon, and in the case of placing a moon farther out, you would double this period. So for instance, if the existing moon has a period of 30 hours, we would double it to make the next moon's period 60 hours. In actual use, you would probably want to go a bit above 2 times, like 2.1, 2.6, 3.2, something like that. Otherwise, your moons will be in a resonance, which isn't necessarily a bad thing, but it does bring up some additional issues, which we'll cover in a future video. Once you've got the newest moon's period defined, you can use this equation, which we covered earlier, to calculate its semi-major axis from this orbital period. If you're placing a moon in an orbit interior to the existing moon, that is closer to the planet, then you would half its period. So in the above example, with an existing moon having a 30-hour period, the interior moon would have a period of 15 hours or less. Just remember to be careful when placing moons closer to the planet and check to make sure that they are above their Roche limit. When converting a moon's semi-major axis from meters into a comparative unit, an astronomical unit is usually too large. Instead, we use the lunar distance, which is defined as 384,400,000 meters. So in the calculator, we simply enter our moon's semi-major axis in meters, and then divide by 384,400,000 to get its orbital radius in lunar distances. Once we have placed our moon, the next parameter we should define is its inclination. That is, how tilted the moon's orbit is relative to the planet's equator. For this parameter, the class of the moon is very important. Major terrestrial moons are likely to have high inclinations greater than 5 degrees due to them forming from collision events, while major jovian moons are likely to have low inclinations, usually below 2 degrees, due to them forming from a disk centered on their parent planet's equator. In either case, the closer the moon orbits to its parent planet, the lower its inclination will tend to be. Inclination is usually measured in degrees, spanning from 0, which is an equatorial orbit, up to 90, which is a polar orbit. It is possible to have inclinations higher than 90 degrees, but that's considered a retrograde orbit. I'll talk more about retrograde orbits in a future video. I'm going to give my major Jovian moon a low inclination of just 0.5226 degrees. Next, we will define our moon's orbital eccentricity, that is, how elongated its orbit is. This parameter is also influenced by the moon's class. Major terrestrial moons are more likely to have high eccentricity orbits due to them forming from collision events, but their eccentricity can diminish over geological time due to tidal interactions. For reference, Luna's current eccentricity is about 0.0549. The eccentricity of major Jovian moons, on the other hand, tends to be very low, with the average eccentricity of major moons in our solar system being approximately 0.0044. However, Jovian moons with above average masses or large semi-major axes can have slightly higher eccentricity. For example, Saturn's major moons Titan and Iapetus have eccentricities of 0.0288 and 0.0277 respectively. Eccentricity is a number below 1, so it will start with 0 point something and should have at least 4 digits past the decimal point, but 8 is better. Since my moon is a major Jovian moon of a gas giant planet, I'm going to give it an orbital eccentricity of 0.00290837. Once you have defined your moon's eccentricity, you can calculate its periapsis, the point in its orbit where it is closest to the planet, using this equation, which relates the periapsis distance to the moon's semi-major axis times the remainder of 1 minus its eccentricity. Similarly, you can calculate your moon's apoapsis, the point in its orbit where it is farthest from the planet, using this equation, which relates the apoapsis distance to the moon's semi-major axis times the result of 1 plus the eccentricity. So, in the calculator, we start by entering our moon's distance from the planet, its semi-major axis, in meters. Then multiply in open parentheses. Type 1, then minus for the periapsis, or plus for the apoapsis, and then the eccentricity value. Then close the parentheses. Your equation should look something like this. The last important parameter to calculate is the moon's sidereal and synodic rotation periods. The sidereal, or true rotation period, will be equal to the moon's orbital period, since the moon is tidally locked to the planet. But its synodic period, which is the measure of its day, will depend on the orbital period of its parent planet. I have a video explaining all of this and how to do the calculations, so I will link it in the card above and in the video's description below. If you wish to also calculate the optional parameters of the moon's orbital velocities, I have a video detailing that as well. The link will likewise be in the description. In this video, we only created major moons, but minor moons are far more abundant objects. So in the next video, I will cover everything you need to know to create realistic minor moons, asteroids, and Kuiper Belt objects. I hope you will join me for that.